Hey students, Mr. Clausen here. Just wanted to go through how to solve a sample problem using the kinematic equations, so the Fantastic Four kinematic equations that we used in, or that we took notes on previously in class. And so how would you go about solving a problem using these as opposed to the method that we've had with the graphs in the past? Give you a couple tips on how to do it. And as you can see, we got the initial scenario, and then I've got a few extra problems here going on this scenario for how to figure it out. So just a reminder, there's 5 variables that I could ask you about. There's 4 equations to do that. If you know 3 of these variables, then what you can do is find the other 2, and then hopefully that would make you a happy physics student. Yep, that's right. I went with that joke here for it. So let's just take a look at what we got going on here. So it says Kelsey throws the ball vertically up into the air, and then it says the ball leaves her hand at a speed of 20.5 meters per second. The first thing I do when I'm approaching this problem, after I've listed down the 5 variables, what I do is I just draw a picture to help me understand the scenario a little bit. And it doesn't need to be like super accurate. You just want to get a couple labels on there. So in this case, it said Kelsey, threw the ball into the air with a speed of 20.5 meters per second. And then the ball goes up. It's going to turn around and come back down. Okay? And so let's figure out what's going on here. What else, other information we can do here? Well, the first thing I want to note is that I do know that at the very tip top of this path, the ball is going to be traveling with a speed of 0 meters per second. And since the ball was in the air, we know that it's always going to be feeling an acceleration equal to that of gravity, which is negative 9.8 meters per second every second, or we can say meters per second squared. All right, so far that's all I've done is just listed or just drawn what's going on in the problem. And now what I'm going to do is start figuring out what the questions are even asking me for. Okay, so the first one here, it says, how long does it take until the ball stops rising? Okay, so in this one, when they say how long, what they're referring to is not length, but they're actually asking us for time. So time is what we're looking for. And then the other key piece of information here, it says until the ball stops rising. Now, what's important about that is that's that point that we had right here. And so we're going to be taking a look at the ball from here to there, just the first half of its little journey up into the air. And why that's helpful is because we can then use the information of it stopping to help us out. So we can say that the final velocity is 0 meters per second. Okay. The initial velocity is 20.5. All right. And then the other information that was given to us, or that we know because this is happening on planet Earth, is that the acceleration is 9.8 meters per second. And what we're looking for in this case is the time. So once we have that listed, even though we don't know the distance, we can still figure this out because we do have 3 pieces of information. So what we want to do is find one of the formulas, one of the Fantastic Four kinematic equations, so one of these guys, and figure out which one has all the information in it that we have, as well as the one that we're looking for. And when I look at them, I know this one's not going to work because it says distance, which we don't know yet. This one doesn't work because it has distance. This also has distance. And so the one we want to take a look at is just this one right here. It says V final equals V initial plus A times T. And so the next thing I always do, and you should do as well, is write down the equation you plan on using. Okay? This just makes it so much easier when we go to plug in our variables. You're less likely to make mistakes when this is going on. So now what we do is we start plugging in numbers where they belong. So according to our list, the final velocity was 0 meters per second. So we're going to go ahead and put 0 in there. The initial velocity was 20.5 meters per second. Okay, we're going to add to that, don't forget the negative 9.8 meters per second squared, and then t. Okay, and now all we need to do is just start rearranging this or solving for time. So the first step I would do in this case is I would subtract 20.5 from both sides. All right, and then I do that over here. If we simplify that down, this goes away. What we're left with then is 20.5 negative meters per second equals negative 9.8 meters per second squared is multiplied by time. So I'm just doing the algebra right now to simplify it. The next step is going to be then just divide both sides by negative 9.8. Okay, the negatives would cancel here, and then we're left with just 20.5 divided by 9.8. So 20.5 divided by 9.8, and we get a time of 2.09 seconds, I guess is what we'll say here. So time is equal to 2.09 seconds. Now, why that's useful for us is we can come back over here. I'll put it in a different color to help us remember that this is one that we calculated out. Is we now know that it takes two seconds to get to the top of the ball's path, which is beneficial because the next question here is asking how high does the ball go? Well, how high the ball goes is talking about, what is the displacement at that point when the velocity final is equal to 0. So what we do then is we just start take a look at what we're looking for now. So in this case, we're looking for the height of the ball, and we have all sorts of information, which means almost any of these would work for us. It provided we look for one that just says change in distance. I personally like this one just because it works a lot. So I think you could use this one, but we'll take this one here. Just like I said, I think it works a little bit easier. All right, so let's go ahead and do it. Actually, what am I talking about? Yes, we could do this one. It does work easier, but let's make it easier on ourselves. This has fewer variables, so we can go ahead and just put this one in as well. So to figure that out, I'm going to use the second one there. I'm going to switch back to red. Okay, so we got this. Like I said, you could use either formula. It honestly doesn't matter. I'm just picking this one because it's got a few less terms to it, and so it might just go a little bit quicker for me when I'm doing it. All right, so delta x is equal to, and then we just plug in our values. 20.5 plus 0 divided by 2 multiplied by the time of 2.09 seconds. All right, so now what I need to do is just bring up my calculator, and we can run that through. I'll just bring it over here to do that. 20.5 divided by 2 is 10.25. Okay. And if we multiply that by 2.09, we get a displacement of 21.42 meters. Okay, so that's how you'd use that one. Now, this is where it really becomes handy, is for this third one here, because it's saying what is the speed of the ball when time equals 3 seconds. Well, if we realize that it's going to take 2.9 seconds for the ball to get up to the top, that lets us know that when the ball comes down, it's going to be located somewhere around here when time is equal to 3 seconds. So what we could do is we could figure out how much time it takes to get to the top, and that would be 0, have that be our initial velocity, and then calculate it down. But the kinematics are super beneficial for us because it doesn't require us to do that, okay? We just don't need to in this case. What I would want to do is I'm just going to use this equation right here, same one we started with, V final equals V initial t plus AT. I'm going to write it down here just so you can see why that's beneficial for us. So we're going to say V final equals V initial plus A times T. Okay? This question is asking what is the speed when the time equals 3 seconds. So in this case, we're going to use time equal to 3, not the one we calculated before, because remember, this was just to get to the tip top. And as long as you're easy with or pay attention to your signs, life goes really smooth. So the initial velocity is still 20.5 meters per second. The acceleration is negative 9.8 meters per second squared. And then what you can do is you just multiply it by the new time that we had, which was 3 seconds. This will give us the final velocity, and that'll take into account the fact that the ball's got to go up, stop, and come back down this is all going to work out. Okay, so I'll pull up my calculator and let's run this through. All right, do I got it? Yep, we're good. All right, so clear that out. 3 times 9.8 would be 29.4. You got to make sure you write with the pen. Now, the negative's important here, so it's going to be negative 29.4 meters per second. And then we have our 20.5 to begin with. Write this down. And so then all we need to do is basically subtract off 20.5, or if you would like, I can do it this way. 20.5 minus 29.4, and what we're left with is 8.9 meters per second. And the key thing to note here is it says it's negative 8.9, and that tracks with what we've been taking a look at, because the ball had to go up. Took 2 seconds to get up there, and then it's only been falling for just under a second for it to get back down. And so it makes sense that its speed's going to be a little bit less than the 9.8 that we had. So there you go. That's how you solve problems with kinematics. Just a reminder, the first thing you want to do is to list the information that was given, include a picture of the scenario, then find which of the kinematics you're looking for. Let me put this back on here. There we go. Which of the kinematics you're going to use, write that down, and then you just plug in your numbers and solve using algebra. So that's that. If you have any questions, I'm always available in class. Otherwise, you can see me throughout the day. Talk to you later.